let us try to take a look at now again the DC generator. In that we are looking at separately excited DC generator. We looked at two characteristics. One is OCC, the other one was basically the external characteristics, and I had just embarked on discussing armature reaction, right? So let me again redraw the OCC. So in separately excited DC generator, we were actually pointing out that EG will be having a non-zero value even with IF equal to 0, and then we are, if there is residual magnetism of course, and then we are going to have it somewhat like this. This is what is my open circuit characteristics, right? And we also showed something called a load line, right? We were talking about basically where is the operating point for this particular case, and we said that if I am going to talk about the rated field current somewhat like this, this is what will be the rated flux as well. So this will be actually my rated generated voltage. This will be the operating point, and we said that this particular thing will correspond to a speed which is corresponding to rated speed when I am driving the generator at rated speed, right? So I would say that the rated EMF or rated voltage of the machine is defined as that voltage that is obtained from your generator when you are passing rated field current through your excitation winding and when you are driving the generator at rated speed. That is what is defined as the rated voltage of the generator, right? And then we were trying to look at if I am having the generator here and I am connecting a load which is a variable load, okay? So we were looking at what is the terminal voltage of the generator, and we were looking at what is the current that is flowing through the load, which is same as armature current in the case of a separately excited generator, right? So I may have my field winding here. Some books show the field winding perpendicular to the armature winding because the brushes are always connected perpendicular to the line. Wherever the field lines are going, generally perpendicular to that the brushes will be placed. So that is the reason why sometimes this is the kind of representation some of the books show. The field will always be shown perpendicular to the brush axis. That is how it will be shown. So I am going to have essentially the field current flowing like this. So I have VF connected here. I may have a resistance connected in series to vary the field current, and this is going to be my RF inherently, and this is going to be R external, the external resistance that I have connected, right? So if this is going to be my external characteristics where I am drawing the variation of what is the terminal voltage with reference to the armature current that I am drawing. If it had been an ideal generator without any drop in the form of resistance drop within the machine, I should have gotten a flat characteristics. But I am not getting a flat characteristic because I am going to have definitely some amount of IA-RA drop taking place. I am showing this in an exaggerated fashion, but this is my IA-RA drop, right? This is essentially because of the internal drop that is taking place within the machine conductors, which are manifesting a resistance of RA. So this is going to be IA-RA drop, which is contributing to, in one sense, the regulation of the DC generator. Otherwise, I should have had the voltage as a constant at 220 volts or whatever. But apart from this, we just introduced one more thing called armature reaction drop, which is going to be somewhat non-linear. It will not be linear because it is playing around with saturation and other things, which are basically the manifestation of any magnetic circuit involving ferromagnetic material. So let us try to look at what is this armature reaction, for which let me try to first of all draw the original field, how this was manifesting itself. So this is North Pole, this is South Pole, and I was having the magnetic field lines going like this basically. This is how the magnetic field lines were going. I am not showing the completing path of this magnetic field line, which will go through the yoke, of course. It will go through the yoke. So this was the original field line. So my neutral axis, if I try to look where the neutral was magnetically, this is what was the neutral axis. And that is where we normally place the brushes. So that if we are actually making the conductors change over from dot to cross current or cross to dot current, that happens exactly along the neutral axis, so that it becomes simpler, because the current is going to be really minimal or almost close to zero at that point, because of which I'm going to have mostly the changeover from plus to minus current or minus to plus current pretty smoothly, because it is drifting from South Pole's influence to North Pole influence and North Pole influence to South Pole influence. So when it is drifting, obviously it will go through a zero. The current will go through zero. And when it is going through a zero, it is always easier to change over. So that's the reason why we are placing the brushes somewhere here. So the brushes are normally placed along this axis, which is perpendicular to the magnetic axis. So we call this as the neutral axis. In one sense, in many of the books, they may say this as quadrature axis. And we call this as the direct axis. So the direct axis is parallel to the field lines that are created by the main poles, North Pole and South Pole, and the quadrature axis is perpendicular to that, which is also incidentally the neutral axis if I am considering only the main field flux. Now initially maybe my conductors, what I have placed here, are just having induced EMF. I have not connected any load. Okay? And if I am assuming maybe the direction of rotation is anti-clockwise direction, this is omega, then maybe I will have dots, verify this, and I'm going to have cross here. Fleming's right hand rule. So you will have dots here and cross here. If this dot and cross currents become pretty much influential, because I have connected probably a load in such a way that I am drawing more and more current. Initially when I didn't connect any load, I was having literally zero current. When I have actually connected a load and I am drawing more and more current by reducing the resistance, probably I'm going to have higher and higher current. When higher and higher currents are coming, this armature conductors will also create a flux. After all, they are also placed in a magnetic core, ferromagnetic core. So they are not going to keep quiet. They will definitely produce a flux. Until now, we ignored it. But now, we'll have to consider. So when we are considering that and what kind of reaction it is going to have on the main flux, we call that as the armature reaction. So the armature reaction is the reaction of the main field flux to the flux produced by the armature conductors, which are carrying current now, when it is not open circuited anymore. Right? So if I consider this, I will definitely have maybe around each of them I have to draw a flux or field line. I will have multiple number of them, but on the whole, maybe I can draw something like this. This will be the total line of, field line, what I will have. And if it is dot, I can say that this indicates the direction of the fingers, how they curve, that is going to indicate the direction of the field line. So I'm going to have the field line in this direction and field line in this direction. Of course, they will go like this. This is how the field lines are going to be, right? Similarly, I should be able to draw the field lines for this as well. I should show them more through the air gap, which will actually be the other way around, right? This is how those things are going to be. So I am having the field lines created by the armature conductors, which are actually going to be, here if I look at it, for example, the armature field line is like this, and the main field line is somewhere here like this. This I am talking about. I am talking about this portion. So I am talking about this portion which I have enlarged, and I am showing it like this. Okay? Whereas, if I look at this portion, if I am looking at this portion, I can say I am having the main field flux like this, and the armature flux is also like this. So this is this portion that I am talking about, which I have enlarged. Are you getting my point? So at some point, the main field flux is directly opposed by the armature flux. At some point, the main field flux adds up to the actual the armature flux. So I would call this as magnetizing armature reaction flux, where they are aiding each other. I would call this as demagnetizing armature reaction flux. There are other portions where, for example, I am having the pole here, North Pole and South Pole, and I am having some conductors here as well, very close to, the pole curvature itself. And there, I am having this dot again and this cross here, and if I look at the flux line here, it is actually perpendicular. It is not neither aiding nor opposing. It is actually perpendicular. So because of which, if I actually look at the resultant here, this is the way I am going to have my main field flux, and I am going to have my armature flux line somewhat like this, depending upon the strength of the armature current, of course. So I will call this as phi main, this is phi armature. So when I actually look at the resultant, I will probably get the resultant somewhat like this. The resultant of the two will look somewhat like this. Whereas, if I look inside the armature core, this is exactly in the opposite direction. So, what I am going to have as the overall flux actually will be somewhat like this. It will actually come as a straight line. It will probably bend like this somewhat. And here it might probably bend in the opposite direction, right? And again I should probably have some bend like this, and then it should go like this. So I am going to have all the lines rather going like this. All the field lines are somewhat going like this. So the armature reaction actually distorts the overall flux. At some point it is magnetizing flux, at some point it is demagnetizing flux, and I will call this as cross magnetization. It is neither demagnetizing effect nor magnetizing effect. It is kind of modifying the magnitude as well as direction. So I call this as the cross magnetizing effect. So the armature reaction essentially creates three effects on the overall flux profile. At some point it is creating a magnetizing effect. So I should have actually seen an increase in the flux. But already I am operating close to saturation. So the increase will not be as much as what I expect it to be. The magnetizing flux will not be able to increase the flux. Let us say I was originally operating at some 1.2 Tesla flux density. Maybe 0.2 is the magnetizing effect and 0.2 is the demagnetizing effect as well due to armature reaction. So I should have had here 1.4, I should have had here 1. Coming down to 1 is very easy, no saturation effect. But going up to 1.4 becomes very difficult because already it is saturated to a large extent. So instead of probably going to 1.4, it may go to 1.25 or 1.3. Nothing more than that. It may not be able to go very high. So the overall effect that is seen is a net reduction in flux. Although magnetization and demagnetization are happening at the two ends of the pole, main pole, you can see that this is essentially demagnetization, this is magnetization. So we are going to have both magnetizing effect as well as demagnetizing effect. The magnetizing effect is not as pronounced as the demagnetizing effect because of the saturation coming into picture. So the net effect is an overall reduction in the flux. If there is an overall reduction in the flux, clearly there will be a drop in the voltage. Whether I like it or not, there will be a drop in the voltage. So this drop in the voltage is what is manifested when I drew the external characteristics. So I would say this is actually armature reaction drop. AR drop. This is what is the armature reaction drop. The armature reaction drop gets more and more pronounced when I have larger and larger armature current, because the effect of the armature flux is really much more influential when I'm going to have larger and larger currents through the armature. That is the reason why you would see clearly, maybe initially it may be somewhat linear, but as it gets to larger and larger currents, the saturation effect is much more pronounced, because of which I'm not going to see any increase in flux at all after some time, but I would see a pronounced drop in the flux due to the demagnetizing effect, whereas magnetizing effect is really not going to be all that visible. So that is the reason why I would see a good amount of armature reaction drop when I am coming to larger and larger armature currents, right? So this essentially is not considered when I am talking only about the armature resistance drop. Armature resistance drop is linear, whereas armature reaction drop is non-linear. It will not be linear because of the saturation effect. So what actually is manifested is, one is there is a drop in the voltage, in the terminal voltage. These are the effects of armature reaction. The second point actually we would see is, please note that originally, because I was having the lines which are horizontal, I was having the neutral axis which was exactly in the middle. Now I have to again drop a perpendicular here, so this perpendicular will come out to be somewhere here. So the neutral axis itself is somewhat shifted. I'm not going to have the neutral axis anymore exactly in the middle of, the North Pole and South Pole. It is coming somewhere, in a tilted fashion. So please remember, I had taken the direction of rotation as anti-clockwise. So the neutral axis is also shifted somewhat anti-clockwise. In a generator, this will happen. In a motor, it will be opposite. So if I am taking the direction of rotation as anti-clockwise, I would have a slight shift in the neutral axis. So I am going to have now brushes are not on the neutral axis anymore. It looks as though it is somewhere to one side. So the actual current transfer, which we call as commutation, is going to face some trouble because of this. Previously, I had them exactly on the neutral axis. So I would not have any difficulty basically to transfer the current from plus to minus or minus to plus. No problem. Whereas now, I am going to have definitely the conductors which are already not carrying zero current will be expected to change over because I have put the brush there. So I am going to have somewhat more difficulty in terms of changing over the current from plus to minus or minus to plus, which we would look with the magnifying glass in greater detail about commutation. That will be the next discussion after looking at different types of generators. So we will look at commutation in a greater detail when we are actually looking at the actual current transfer from one commutator segment to the next commutator segment and so on and so forth. We'll be looking at it in greater detail. Yeah. The sparking occurs to some extent because of this, to some extent because of the fact that the machine conductors have inherent inductance. The inductance will not have any effect if it is carrying a steady current. But I am looking at the current transfer from plus I to minus I when the conductors are defecting from the south pole side to north pole side. So if I am having actually no current at all being carried by the conductor when they are transported from the south pole side to the north pole side and vice versa, I would not have had any LdI by dt. But if I am transporting the conductors when they are already carrying some current and I am actually pushing them from the south pole side to north pole side, here you go, you push them, then LdI by dt is not going to keep quiet. It is going to say, I will carry the current for some more time, no matter what. So it is going to carry the current for some more time under heavy opposition from the main poles. And that will essentially spill over into the surrounding air. There will be a larger voltage induction. LdI by dt will manifest itself, and that is essentially manifested in the form of sparking that occurs in the DC machine. Right? That is why the sparking increases whenever there is a higher armature current. The sparking will increase when there is a higher speed as well. If you increase the speed, you are asking the changeover to take place faster and faster. dt is decreasing. You are looking at LdI by dt. I is increasing, you will see increase in sparking. dt is decreasing, you will see increase in sparking. Both will contribute to sparking, right? We will look at this in greater detail when we are discussing commutation. So much so for the armature reaction. Right now, just the last mention, wherever we are having this dot, if we can have some kind of compensation for that dot by having a cross, can I have some winding there, which will immediately nullify the effect of armature reaction? If I can do that, nothing like it. All this armature reaction is null and void. So, normally in many of the machines which are very, very fussy about armature reaction, we might put some conductors. So, this is my pole. I may place some conductors which are known as compensating windings. They are compensating for the armature reaction flux, which are cross-magnetizing in nature. I'm talking about only cross-magnetization because the cross-magnetization takes place along the curvature of the pole. So along the curvature of the pole, if I put some windings along with the pole itself, and if I place them, but I want them to carry a current which is in anti-series with the armature current. So if the armature current is a dot, this will be carrying cross and vice versa. So they will be in anti-series with the armature. So I would have cross as the current here. If I am having dot in the armature conductor. So please understand the connection. You are having the armature conductors which are placed in the rotor. The armature conductors connections are brought out through brushes, through the commutator and brushes. From the brush, the compensating winding will be connected, but in anti-series. So if I'm having, probably it is wound in a particular way, it should be manifesting itself with the dot and cross in the opposite sense to that of your armature current. That's all. So they will be connected in series with the brushes themselves, normally. So if I am carrying only 5 ampere of armature current, I want the compensating winding also to create a flux only corresponding to 5 ampere. So I don't want them to carry a constant current, I want them to carry whatever is the armature current, exactly. So it will be connected in series with the brushes, normally. The same thing will be done for the other pole as well. So if I am having, this is north pole, if I am having south pole here, I would again have compensating windings here, which will be carrying, for example, dot, if I am having crosses here. So this is essentially known as compensating winding. Yeah. It is on the stator, but it will be connected in such a way that it carries armature current, which is rotor current. Compensating winding will be along the pole curvature. It will be placed along the pole curvature, and it will be essentially carrying a current in the opposite sense of the armature current, so that it will be nullifying the armature flux cross-magnetizing effect, right? We will also have something called interpoles, which are smaller poles, which will be either nullifying the magnetizing effect or nullifying the demagnetizing effect. Please remember that the magnetizing effect and demagnetizing effect always take place along the Q axis, on the D axis. So D axis, along the D axis, to nullify the cross-magnetizing effect, we put compensating winding. Along the Q axis, in the interpolar region between the two poles, main poles, we place something called interpole. So if the armature reaction is creating a magnetizing effect, I will create a demagnetizing effect with the help of interpole and vice versa, right? So to come back to the effect of armature reaction, there is a reduction in the terminal voltage. That is the first point. The second one is neutral axis gets shifted. The neutral axis gets shifted, right? That's what we saw. So both these things can be eliminated if I have compensating winding and interpoles. They will essentially make sure that the armature reaction effect is completely nullified if I have appropriate design of interpole and appropriate design of compensating winding. In which case, again the neutral axis will be back to normal, the commutation and everything will go on pretty smoothly. So wherever I cannot tolerate sparking, generally we tend to avoid DC machine itself, if it is possible. Still, if I have to use DC machine for some reason, then I might like to put compensating winding and interpole, although all of them become generally much costlier. If I buy a DC machine without these things, it will be less costly as compared to when I buy it with compensating winding as well as interpoles. It will be definitely costlier. So now that we have kind of completed the armature reaction and its effect in the case of a separately excited DC generator, let us quickly look at the first self-excited generator, which is a shunt generator. So the self-excited generator, as the name indicates, you are not going to give a separate excitation at all. No power supply available. All you are doing is just driving the generator, and it has to produce electricity. No excitation you are giving, right? Sounds pretty cool, right? So you are not going to really provide any electricity at all to start even the magnetization. So what you will do in this case is, you have the armature here, right? And then you are going to have the field coil here. You are not connecting any supply. You may connect a load here. That's fine. Initially you will have some residual magnetism. It will produce a small voltage. That voltage will circulate a current through the field. Are you getting my point? Residual magnetism, let us say, is producing a small voltage of 15 or 20 volts. So this is going to circulate a current through the field. Initially I may not even connect the load. I'll say let the voltage build up, then only I will connect the load. Until then I will not even connect the load in all probability. So I will have a current flowing through the field that will actually make the current more than zero. Definitely, originally it was zero current, residual magnetism that was producing a voltage. Now that voltage will circulate a current through the field. Let's assume that that current is going to create a flux which will aid the original residual flux. So the flux will increase. More voltage, more current, more flux, more voltage, more current, more flux. It will simply build up further and further. It should have hit infinity, but saturation comes into effect. So the flux cannot go beyond a particular value, and then you will see that basically you are going to see the voltage is building up, but it reaches some value which is dictated by where I am going to have Vf equal to Eg equal to If Rf. This is If, this is Eg. Right? So let me say Eg1 probably. So this corresponds to Eg1. Right? So you are going to see that this happens until it reaches an operating point which is corresponding to Eg1, which will be the point where the field voltage and the armature voltage balance each other. They are connected in parallel. So they are going to balance each other, right? At a given speed, whatever is the speed at which I am driving the generator, right? We'll continue with the self-excitation process in the next class.